Hello, friends. Today we're going to talk about the ideal gas laws and how they lead us to the first law of thermodynamics. The first of the ideal gas laws is Boyle's law. Boyle's law tells us about the relationship between pressure and volume of an isolated from its surroundings sample of gas at a constant temperature. Now, what does it mean for a gas to be isolated? Most likely confined to a container. In fact, you'll sometimes see this restated with the word confined instead of isolated. The relationship described is that if you keep the temperature constant, the volume of a gas will be inversely proportional to the pressure exerted on the gas. Well, what does that mean? If you want to kind of state this in like normal person terms, it would probably be if you give particles less room to move. So you take the volume and you make it small. Well, you've given those particles less room to move. They're more likely to hit each other and the walls of the container. So they will collide with the walls more frequently because there are fewer places for them to be that aren't right up against the walls. And then if we were to state this relationship as an equation, then keep in mind temperature would have to act as a constant of proportionality. So if you have a volume before and a pressure before and a volume after and a pressure after, in order for Boyle's law to allow you to predict whichever variable you don't have, you must have the temperature be constant. And if that is the case, your initial pressure and initial volume, since they're inversely proportional, this one goes up and the other one would have to go down. And we end up with P final, V final. Some people write this as ones and twos instead of initial and final. I'm just trying to keep this constant between how you learned formulae in AP1 versus AP2. Seems like the 1-2 switch would, it's a little late in the game to be changing how we write formulae. But if you see it with ones and twos on your equation sheet, just whatever, who cares? And again, I cannot stress this enough. This works as long as you have a constant temperature. We even have a word for constant temperature processes that act on a gas. And iso, from the Greek isos, that should not be dotted for iota. What am I thinking? And therme, isotherme, as in uh, solitary heat. So this is isothermal. And an isothermal process is one in which the temperature does not change, or if you wanted to define it mathematically, it is something that happens to a gas where delta T is 0. Easy stuff, or at least hopefully. Right, buddy? Okay. For example, An isolated 1.53 liter sample of sulfur dioxide, that's the gas that comes out of volcanoes and car exhaust. It's also the like uh, stuff that keeps reacting with the clouds in Venus to cause acid rain. I guess the same thing happens to a less exciting degree here on Earth. But sulfur dioxide gas at a pressure of 5.6 times 10 to the 3 Pascal, or 5.6 kilopascal, if you'd rather write it that way, is changed such that its temperature is the same, but its pressure becomes 1.5 times 10 to the 4 Pascal, or 15 kilopascal. What is its final volume? Well, the fact that the temperature did not change means that we have permission to use Boyle's law for this one. Let's take Boyle's law and we'll just go ahead and put it here since we know this is what we are going to use. But now with the 3-bracket method, this is a measurement of volume, 1.53 liters of space taken up. Doesn't necessarily matter that it is sulfur dioxide. This could have been any other gas, but sulfur dioxide is interesting. Pressure initially is 5.6 times 10 to the 3rd Pascal. And it has changed, so the temperature is the same. So delta T is 0. You have permission to use this isothermal process descriptor. Final volume is our unknown, and our final pressure is 1.5 times 10 to the 4th Pascal. If pascals and liters are unfamiliar units for you, don't get pressed. If you notice, this proportion, like if we put liters in and liters in, it's just going to cancel. It's going to be on both sides of an equal sign. It'll go away. So if we put pascals and pascals in, it's just going to cancel anyway. So if you didn't know what pascals are, whatever, you could have used any pressure unit as long as you use it on both sides. We will talk more about Pascal if you just give me a minute. But before that, let's plug in. V final needs to be by itself, so we'll move pressure final to the other side. Pi VI over PF. And then that would be 5.6 times 10 to the 3rd Pascal times 1.53 liters divided by 1.5 times 10 to the 4th Pascals. As I promised you only a moment ago, not that you believed me, but I would never lead you astray. Pascals over Pascals cancels, leaving us with just liters. So the same unit that we put in, we get back out. Punch all that into your calculator, and you should find that the final volume is 0.57 liters. At this point, you pump the brakes and you think, does that answer make sense? Well, what did the pressure do? It was increased. If the pressure was increased, and according to Charles' law, it is an inverse proportion between pressure and volume. If pressure goes up, volume goes down. You're squeezing the gas harder, it takes up less space. You are compressing it, and then it fights back. But I told you we would talk about these units, so let's go ahead and do that. For future classes, they will already have had fluids in AP1, but for the 2024 to 2025 class, you never got fluids, so you might not have ever heard about pressure in the physics class anyway. Pressure is why, even though a football player who is attempting to tackle you has lots and lots more momentum than a bullet, you'd probably rather get tackled by the football player. The football player, when they exert that impulse against you, is going to spread it out over, a broad area, and it's going to apply it more or less evenly across where that's applied. If their shoulder goes into you, then you have all of this area hitting you. So they may have an immense force, but it's spread out. A bullet may have a much smaller force due to having a tinier momentum to impart an impulse, but it's got a point on the front. So all of that force is against one single point, and that much force on one point is enough to break the skin and the muscle and the organs all in the way. That's the difference between force, just pushing, and pressure, pushing on a specific area. So pressure is a ratio comparing force to the area over which it is exerted. That description makes the formula really easy to guess what it is. The only thing you would need to know is what the symbol is to put in for pressure. And unsurprisingly, it's a capital P. Don't get it confused with the capital P for power. But pressure is force over area. And our units for that will therefore be newtons of force per square meter of area. There's a joke about Einstein, Pascal, Watt, Joule, and Newton playing hide and seek. Einstein is it. He counts down, ready or not, here he comes. So Einstein looks and he immediately sees Newton. Newton didn't even attempt to hide. He just took out a piece of chalk and drew a square around himself. Einstein says, "Well, I guess I found you, Newton." He's like, "No, you found 1 Newton in a square meter. You found Pascal. He's it." I didn't say it was a good joke. I said it was a joke. But newtons per square meter are otherwise known as pascals of pressure. So newtons per square meter, and then capital P, lowercase a for your pascals. The imperial units for pressure that you will hear about quite frequently are pounds of force per square inch of area. PSI, pounds per square inch. But still, force over an area unit. If you want to be non-denominational about it, neither metric nor imperial, but colloquial? Or maybe just an earth chauvinist. There are atmospheres of pressure. Atmospheres of pressure are based as treating the Earth's atmospheric pressure at sea level, standard temperature, as one unit based on the planet. There are also torrs of pressure or millimeters of mercury, but who cares? Atmospheres you will actually see in this class, so they are worth going over. An Earth atmosphere is about 15 psi, or about 101.3 kilopascals. I think that might be on your equation sheet. Double check it. I'm not promising that one, but I think it's on there. Again, this is an Earth chauvinist unit, not that any physicists who speak the language we're speaking now have ever lived anywhere else. But for perspective, I mentioned the Venusian atmosphere before. The Venusian atmospheric pressure is 92 atmospheres. So if you wanted to find how many pounds per square inch get exerted on you by this thick, dense Venusian atmosphere, take that 15 psi, multiply it by 92, or this 101.3 kilopascals and multiply that by 92. You can imagine that if an astronaut was ever to go to Venus, they would not use the usual inflatable spacesuits where you are pumping it full of air to keep pressure on your astronaut. You would want them in a hard suit, like an Iron Man suit, in order to keep that pressure off of them, like more like a submersible at the bottom of an ocean. In fact, if I remember correctly, the Venusian atmospheric pressure is comparable to what you get about 800 meters below the Earth's uh, sea level, with all that weight of water coming down on you. Don't hold me to that number, but for some reason, 800 seems right. The Martian atmosphere is barely there, a thin, tenuous layer of carbon dioxide at 0.006, so 0.206, so 0.6% of the Earth's atmospheric pressure, so 0.006 atmospheres. You want to find out how many psi that is? One Earth atmosphere is 15 psi times 0.06. So atmospheres. And the other unit that appeared was a volume unit. Honestly, you better know volume by now, or I'm going to have to go and fight your math teachers one by one. But volume is the amount of space taken up by an object. The symbol is a capital V, and your units are going to be either cubic meters, if you were doing meters by meters by meters, or liters. Now, those are not equivalent like newtons per meter and pascals. Liters are otherwise known as cubic decimeters. So the liter is, or yeah, it's still defined this way. If you take 10 centimeters in the z-axis, and then 10 centimeters in the x, and you make it in the z-axis 10 centimeters tall, that's 10 by 10 by 10. Well, 10 centimeters is 10 hundredths of a meter. That is a tenth when you do that cancellation. So decimal, decade, a tenth of a meter. So you take a tenth by a tenth by a tenth, make a cube, that's 1 liter. Between those two, if you needed to convert 1 cubic meter, well, a tenth by a tenth by a tenth, how many do you think it takes? 1,000 liters. Interestingly, you see a lot of the smaller metric prefixes applied to liters in common parley, but not a lot of the ones for the big amounts. You don't often see kiloliters or megaliters. Why? Because 1 kiloliter would just be a cubic meter. You just swap the units so you don't have to say kilos. I don't know. But instead of ever having kiloliters, you just go straight to the cubic meters if you're talking about it like that. However, deciliters, centiliters, and especially milliliters are all very common. All right, moving on from Boyle's law, which works when you have constant temperature, to Charles's law, which works when you have constant pressure. Charles's law is the relationship between volume and temperature of an isolated gas at a constant pressure. What is that relationship? Well, the relationship is such that the volume of a confined gas is directly proportional to its temperature. Again, that is assuming that pressure is kept constant. Again, pause and translate the physics and math stuff into normal spoken language. What does this mean? It means that as you raise the temperature of the gas, the molecules start going faster and faster, and then they're hitting the walls of their container harder and more frequently and more energetically. But that is contained. If that was the case, where they're hitting harder and harder and harder, you would imagine the pressure would go up. If the pressure is not going up, then something else must keep them from beating against the walls. What is happening? The walls move away from them. So, for example, if you take a rubber balloon full of air and you put it in the microwave for a couple of seconds, it expands to fill the microwave oven chamber. Or if you put that same rubber balloon full of air in the refrigerator or freezer, it would begin to shrink, not because it is leaking out air, but simply because the air is becoming smaller. As the temperature drops, by direct proportion, the volume drops. And in Florida, we really only have to deal with this at the change of seasons. Usually around November to December, drivers in Florida realize that their check tire pressure light comes on. Why? Are their tires leaking? Do we all just get our tires slashed by our stalkers in December and there's like a union thing where they have to do it at the same time? No! As the air around the tire cools, the temperature inside of the tire eventually drops. And as that gas confined inside that tire drops, it takes up less space inside of the tire. You may have seen videos on the internet of people using like hairspray and a lighter as like a makeshift flamethrower to suddenly reinflate a tire. Charles's law. This is what happens also with like hot air balloons. You heat the air up, it expands, spreads out, and becomes less dense. And because it's less dense, you get a buoyant force on it. What does this look like in math? Well, probably exactly like you'd imagine. For two things to be directly proportional, there you go. Constant pressure means that this process is not isothermic. We would call this process isobaric, meaning that the change in pressure is zero. Just introducing vocabulary. Quickly, kids, you will run into a problem if you play fast and loose with your units with Charles' law. Let's take an example And quickly, the folly of using the wrong units. Whereas in the last one, they just canceled out. You spit out the old ones on the other side. That ain't going to fly here. Watch. A sample of gas at 15 degrees Celsius and 1 atmosphere of pressure has a volume of 2.58 liters. What volume would this gas occupy at 3 degrees Celsius and 1 atmosphere? If you leave it in Celsius, you will get this wrong. Because if you leave it in Celsius and look here, what happened to the temperature? It was cut down to 1/5. If you attempted this experimentally, you would find that the change in volume is nowhere near 1/5. It wouldn't change very much at all. How could that be? Because you're using the wrong way of measuring that temperature. It looks here as though the temperature has changed down to 1/5 of its original value. But has it? Your initial temperature is 15 degrees Celsius, but Celsius includes negative numbers. If you were to add 273 to this, you would get 288 Kelvin. If you take the final value for the temperature, 3 degrees Celsius, and you add 273 to that, you get 276 Kelvin. And something quickly jumps out at you. It didn't get cut down to 1/5. It barely went down at all. And now you understand why experimentally the volume would barely drop at all. You have a tiny change, and directly proportional to that is a tiny change. One atmosphere minus 1 atmosphere is 0, so we have no change in pressure, confirming that this is an isobaric process. And for reasons that I just explained, it might be a good idea to write it over here in your notes for Charles' law, and really for the ideal gas laws in general. It's the best thing. Use the absolute scale for the temperature. So if you are metric and civilized, you would use Kelvin. If you are barbaric or just evil in soul, you would use Rankine. But it would have to be an absolute scale. Fahrenheit or Celsius aren't going to cut it here. VIVF, TI, TF. That shouldn't have connected, but don't hold that against me. Plug in your values. 2.58 liters divided by 288 Kelvin equals, I don't know, divided by 276 Kelvin. Pump the brakes. The temperature drops. If the temperature drops and the volume is directly proportional, we better get an answer that is smaller. Looking at the size of the decrease, very slight, so I wouldn't expect this volume drop to be too big. Move your 276 to the other side, and Kelvin over Kelvin won't last very long, leaving us with just liters. And VF. Why did I put a question mark here? It's unlike me. It's probably because Boba is over here distracting me. And 2.47 liters. As I suspected, a small drop in one is directly proportional to a small drop in the other. So we've explored a isothermal process and an isobaric process. The next logical choice, we had temperature stay the same, we had pressure stay the same. The next one should be that the volume stays the same. And what would that be? Isochoric. What is our relationship for an isochoric process? The Gay-Lussac's law. Am I pronouncing that correctly? Go ask a chemistry teacher. The Gay-Lussac's law is the relationship. Susie's behind me in her tank, moving around. Anyway, the relationship between pressure and temperature for a confined gas at a constant volume. What is the nature of that relationship? Well, let's mull it over. If you keep the size the same and the temperature goes up, so you're not allowing it to spread out, then if those particles are speeding up and the walls don't get any further away, we should expect them to hit them more often and with more force. By Newton's third law, the walls of the container push back equally hard, creating a greater pressure in the gas. What proportion is that? Well, one thing got bigger, the other thing got bigger. That is a direct proportion. If you wanted to put that into layman's terms, you might describe it as kind of how I did. Since temperature is your average kinetic energy, or at least is proportional to your average kinetic energy, with more kinetic energy, you get more frequent and more violent collisions with the walls, unless they move away. What does this look like as an equation? Exactly what you think it looks like as an equation. Like the last one, but with different letters. Pi over Ti equals Pf over Tf. And this, as I said a moment ago, is an isochoric process. And since it is an isochoric process, delta V equals 0. All right, that is 3 down. We have all the relationships between temperature, pressure, and volume the same. Like we've got them like sewn up. Don't worry about them. However, there is one more thing that can cause a gas to take up more space. You could keep the temperature the same. You could keep the pressure the same. You could keep the, I guess that's it. Those are the two things that you keep the same and have this change. But if you're going to have it take up more space, if you're going to have the volume go up, but you don't let the temperature or pressure change, how can you accomplish that? Easy. Just add more gas. And that brings us to Avogadro's law, our final one when describing your ideal gases. Avogadro's law is the least mind-blowing of them all. If you want to keep the temperature the same and the pressure the same, yet still have the gas take up more space, you could just add more gas. The volume of a gas at a given temperature and pressure is directly proportional to the quantity of the gas. If you need me to explain how to put this into layman's speak, then you're hurting. More gas takes up more space. As math, what does this look like? Kind of unexciting. Direct proportion, VI over NI, where N, that lowercase n, is our number of moles of the gas. A unit that I really, really hope sounds familiar from chemistry, but I will do my best as a non-chemistry guy to uh, summarize. N is the number of moles. Moles are a unit for describing amounts of stuff that is independent from how much space it takes up, or how much weight it has, or how much mass it has. Uh, the the goof of what's heavier, a kilogram of steel or a kilogram of feathers? Well, they both have the same weight, but is it the same amount? A kilogram of steel would like fit in your hands. A kilogram of feathers, you're going to need to probably get like a really big bag. So, are they the same amount? They have the same mass, and mass is the amount of matter in an object, right? But simply put, you got to have more feathers, at least by volume. Is there a way to talk about amounts that is neutral to those two things? Well, consider you have one molecule of water. You have one molecule of diatomic hydrogen. That's water without the oxygen, basically. We know that adding that big extra nucleus to this in the form of oxygen, the water molecule must be bigger than the hydrogen molecule. Yet, if you've got one molecule each, isn't that the same amount? Moles are a measurement of amount of particles, not strictly how much mass or how much volume, but amount of particles, be they atoms or molecules, there are in a substance. If you ever see this with a big N, a capital N, that is when they're skipping the moles and going straight to the number of particles because they are assuming that you did not pay attention in chemistry class. If you need to go from one to the other, then what you use is N naught. Some people would write this as N subscript A for number of Avogadro. I do N naught, but if you ever see N subscript capital A, same thing. I don't know how it's written on your formula sheet off the top of my head, but N naught is Avogadro's number, or Avogadro's constant, if you prefer, and that is 6.02 times 10 to the 23rd inverse moles. What does that do? It allows you to turn a number of particles into a number of moles. Every mole you have of water, kilogram feathers. If you have 1 mole of water, you have an Avogadro's number of water molecules. If you have 1 mole of hydrogen gas, you have 1 Avogadro's number of that gas. So it's a very neutral way of describing amount of stuff. Number of particles is just your number of moles times Avogadro's number. This constant is on your equation sheet. This conversion is not. It's all right. Avogadro's law is pretty easy to wrap your head around anyway. But we got four laws here. Are you going to have to memorize all of these? Well, I expect you to memorize them conceptually, maybe not naming them, but definitely the ideas that they impart upon you, especially the layman's translations for each. That better get into your mind, even if this doesn't necessarily. Well, then why did I write them out? Help drive the point across. And besides, they were written out separately, but the beautiful thing is, you don't need to know them all separately. Why? They've been effectively combined. The four ideal gas laws, like the lines that form Voltron, have been combined. Avogadro's law formed the head. Charles and Boyle's laws are the torso and arms, and the legs come from the Gay-Lussac's law. And together, with their forces combined, we get the most ideal gas law. Usually when people say it's singular, the ideal gas law, not plural for laws, this is what they mean. PV, you're having flashbacks to chem class right now, equals NRT. This is a single state descriptor. Notice there's no initials and finals. So it is at a pressure, it is at a volume, it has an amount, it has, well, this is just a constant. That's a feature of the universe, not necessarily of the gas. And then you have a temperature. This is a single state descriptor, not a multi-state comparison. But it's really good at describing one state. R is new to us, and it is the ideal gas constant. It has a value of 8.31 joules per mole Kelvin. That is how it is listed on your equation sheet in metric base units. But if you are feeling saucy, you could throw some extra units at it. 0.08206 liter atmospheres per mole Kelvin. Probably better just put everything into metric base units, but whatever, there it is. I think a reasonable expectation with this to be would be, how do we get from this, which describes a single state, how do we derive a multi-state comparison from a single state equation? Well, this is true for any ideal gas. It should still be true after that ideal gas goes into a new state. Thus, if we take PV equals nRT, let's take whatever we don't want to change. This is true for our universe, so I wouldn't imagine it would change. And also, let's say we keep the amount of gas the same. We block them off, and we will refer to this combo meal as a constant of proportionality. So if that's going to be our constant of proportionality, it will be the thing that remains true even if the rest changes proportionally. So set it off to one side. And we get that this will be true in the before state and the after state, as long as we don't change the amount of gas or what universe we're in. So if the initial values are equal to that, then the final values are equal to that. Simplifying it down, you get this comparison. There you go. That's how you would use this to arrive at one of the others. Now, if you were trying to get this to not just be all three written here, but you wanted to get Charles' law or Boyle's law out of it, what do? Well, you plug in the same thing twice and it's on either side of an equal sign and it cancels out, leaving you with the law in particular. In some cases, you might be asked about number of particles instead of number of moles. That might be more convenient in a couple of cases. So if you are trying to avoid moles because you are having flashbacks to your chem class, and that was traumatic for you, and I know it was for some of you, well, here's how you can get rid of the NR and get around moles entirely. PV equals nRT. But as we discussed a moment ago with the Avogadro's number thing, if we take n and move Avogadro's number to the other side, we can get big N divided by n naught, and that's worth little n, your number of moles. So there is a substitution that gets rid of little n. We are no longer working with moles, but we can do even better than this because these two constants form a combo meal of their own. The gas thermal constant, I think it's called. Most people just call it the Boltzmann constant, but R, our ideal gas constant, divided by Avogadro's number, is replaceable with just another constant that is on your equation sheet. Lowercase k, subscript b for the Boltzmann constant, T. So R over T turns into k subscript b, the Boltzmann constant. As I said, this is on your equation sheet. Don't worry about memorizing it. Just know that you should use it when you need to use it. In fact, both versions of the ideal gas law are provided for you. If you look at your equation sheet right now and omit this part in the middle with the transforming of constants, PV equals nRT equals N Boltzmann constant T is how it's written on your equation sheet. You get both. And they didn't always do that. Remember, work could be defined as delta E or as force distance cosine theta. They only gave you one, and the bonus definition they just expected you to know. Well, in AP2, I guess they're a little bit more generous with you. Let's do an example. It'll take some writing, but bear with me here. Whew, that took some doing. In the lungs, a thin respiratory membrane separates tiny sacs of air. The air is at 1 times 10 to the 5 pascals from the blood in the capillaries. These sacs, called alveoli, are the source of oxygen for your blood. The average radius of one of these sacs is 0.125 millimeters, or I guess that's 125 micrometers or microns. And the air inside contains 14% oxygen. That's not a feature of your blood. That's a feature of the planet we're on. 76% of our atmospheric gas is nitrogen gas. 14% is oxygen. Depending on where you are, actually. Whatever. Assuming air behaves as an ideal gas at human body temperature, 310 Kelvin, find the number of oxygen molecules in one of the sacs. Number of molecules. Are we using big N or little n? They didn't ask for moles. We're using big N. So that is our unknown. Our pressure is 1.00 times 10 to the 5th Pascal. These sacks have a radius, but they are three-dimensional objects. What shape is that? It's a sphere. Personal trauma has forced me to memorize the volume of a sphere equation. However, if you don't have this memorized, the volume of a sphere is for some reason on your equation sheet. So there you go. Plugging in a radius, now this is in millimeters. Turning our millimeters into meters is very easy. Milli just means times 10 to the negative 3. So plug in 0.125 times 10 to the negative 3 into 4/3 pi radius cubed, and you should find that the volume inside of one of these sacks is 8.18 times 10 to the negative 12 cubic meters. Not a lot of space. Doesn't need to be. Your lungs are full of them. There's enough of them in number to make up for the small sample size. T is 310 Kelvin, the absolute temperature of a human body, and the Boltzmann constant is 1.38 times 10 to the negative 23 joules per Kelvin. I'm just now noticing that up here, for some reason, I wrote joules per second, which would just be watts. It's joules per Kelvin. Better late than never. You can't blame me. Both of my pets are scratching around behind me. Susie, I think, is about to shed, and Boba is howling at me, wanting my attentions. PV equals big N, Boltzmann constant, T. What is our unknown N? So we set N off by itself, and it's going to be PV divided by the Boltzmann constant times the temperature. Plugging in for that, so this is plugged in straight up. But remember that pascals could be rewritten as newtons per meter, and it's the same thing. If we look at our units, newtons, you right? You guys hearing this? Yeah. Got him. All right. Boba, help me out. Everyone say hi, Boba. So newtons times meters is joules. So Newton, and then one of those meters we can replace with joules. We got joules in the top and bottom, it goes away. Meters over meters goes away. And Kelvin over Kelvin goes away. Did I lose track of a meter somewhere? What do you think, buddy? I did lose track of a meters. Newtons per meter is not pascals. It's newtons per square meter. How did I forget that incredible joke? So that gets rid of all of our units. We don't have any units left. So what do we get? We just get a number, a counting number. Counting numbers don't strictly need units. How many apples do you have? You don't have 5 kilograms apples. You have 5 apples. It's just a number. So we just get a counting number. And what counting number do we get plugging all of this in? You will find that the number of particles in the alveoli are 1.982 times 10 to the 14. That is a lot of particles, but is that the amount of oxygen molecules in one of these sacs? No, it is not. That is the total amount of particles, only 14% of which are oxygen. So what do? We multiply by 14%. And we will find that there are 2.677 times 10 to the 13 particles of oxygen in one of those alveoli. Relatively powerful stuff. That's a lot of oxygen in just one of these, of which there are many inside of your lungs. It's unsurprising that the every breath you take, like statistically, one of those oxygen molecules passed through Marilyn Monroe or through a T-Rex. Like there's so much oxygen bouncing around, and we take so much in at once and expel so much of it at once, and we're doing that for such a long amount of time. Incredible odds end up playing out. Look, children, while all of this is neat, how do we use it? Perhaps you know that engines work by burning gasoline to make heat, but how does that heated gas, produce the work of turning a tire and increasing angular momentum? Well, for those of you for whom all of this sounds extremely familiar from your chem class, you might recall the first law of thermodynamics being a statement of the law of conservation of energy. That is, energy in an isolated system cannot be created or destroyed, the boring stuff. We used that in AP1, the good stuff, to create equations that related an object's energy to changes. So if an object has a certain amount of potential energy and a certain amount of kinetic energy, we can put that together to find the total energy. And then that stays the same as long as there's nothing doing work on it. And we use this for the Joler coaster, which by some miracle was last year's FRQ 2 days after I went over it. There's somebody at College Board that I owe a beer for that one. But if the total did not stay the same, does that mean we violated the law of conservation of energy? No, it wasn't created or destroyed. It just came from elsewhere. It moved from someplace to someplace else. So we arrived at the truth that any change in energy was work. This is all mechanics stuff. And to be fair, I say heat engine, who works on that? A mechanic. But we are in the thermodynamics section of this course. So what would these ideas look like in thermodynamics language? Well, for one thing, we're going to repurpose some of these letters because there's only so many in the alphabet. So when we say U, that means internal thermal energy. So if there is any change in internal thermal energy, how could that have been accomplished? Well, I can think of two ways. How do you get something's thermal energy to go up? Add heat. Q equals mc delta T, or you use conductivity, convection, whatever. Heat is applied to it. It flows in from its surroundings. Or work could be done on it. Like, say that you increase the pressure of a gas, you squeeze it, you used a force to push those particles together over distance. That's work. Work is an increase in energy. And as we already saw, it makes the temperature go up if you squeeze a gas. So that must mean that our delta U would be positive. This statement right here is how we in this class would state the first law of thermodynamics. Remember that laws in science are not rules that you are not allowed to break. They are mathematical descriptions of how stuff works. Math in science is a law. It's not like a theory can get enough evidence behind it to have a law of evolution by natural selection. That will never happen. You could have a description of the rate of evolution, and you might be able to make a law out of that. You're right. But the law of thermodynamics, we could say it here. This is a mathematical descriptor. It's just often useful when you are trying to wrap your head around it, just like the other laws where I put them into words in order to make the math make more sense. So if you've ever heard that the first law of thermodynamics is just that energy is conserved, oh, that's the reasoning at which you arrive at this. But really, it's that any change that is against that conservation, any change in a system's internal energy cannot be blamed on creation or destruction. Any change in a system's internal energy must instead come from the exchange of heat or work with its surroundings. I've mentioned work being force times distance cosine theta a couple times. Let's go back to that. Weren't those simpler times? Work is force times distance. And the cosine theta thing just makes sure that you are in the same plane. So the force application has to be parallel to the distance it moves through. So the normal force doesn't do work on a book sliding across a table, but frictional force does. Old stuff, but good stuff. Another thing dealing with force is pressure. Pressure is force over area. If you move that A to the other side, we get AP equals F, a descriptor of some of your grades. If we make a substitution here, we can put in place of F for force, area times pressure. And we can get pad. Great. We pressure times area times the distance. But if you imagine like a plunger on a syringe, here is the area. You move the plunger through a distance in order to squeeze these gas particles together. That area and that distance, that's a cylinder. You squished the cylinder. How big of a squish was it? How big is that change in volume? That's correct. It would be the area times the distance it moves through. Thus, we can take these and we arrive that work must be pressure times the change in volume. Now keep in mind, what is changing here? The volume is changing. The pressure is staying the same. And what word describes a process in which the pressure is constant? Isobaric, as in barometers used to measure pressure. Now, work could be done on a gas if you squeeze it, but you could probably also imagine the gas, I don't know, let's say it is really high pressure and your plunger on the syringe pops back out. Well, that is work being done by the gas. One is in, one is out. In and out implies directionality. And where we have a vector with a direction, we need to define some conventions. Usually, up is positive, down is negative. Sounding familiar? Forward is positive, backward is negative. Counterclockwise is positive, clockwise is negative. Again, we encounter a convention. It could have gone either way, but this is how people have arrived at it. By convention, positive work is done on a gas by its surroundings. Negative work would be done by a gas acting on its surroundings. So if you push the plunger down to squeeze the gas and heat it up that way, that is positive work. If the gas was so hot that it had to expand and that pushes the plunger up, like what happens in a car's engine, that would be considered negative work on the gas or negative work being done by the gas. So the gas is losing its energy in order to use that energy to give something else kinetic energy by moving it. So when the piston expands because the gas inside is heated and its volume increases, well, the top of the piston can be attached to a thing, and usually it's an actuator that pushes forward from being pushed up. And you can use that moving back and forth to turn something. A heat engine is extracting work from the gas. So we would consider that negative from the perspective of the gas, a loss. Remember, energy doesn't have a direction. Energy is a scalar, but a difference in energy can absolutely have a sign as a gain or a loss. But that sign will need to agree with, say, the force imparted or the change in volume. If you have a drop in volume, shouldn't that be a negative delta V? Another way of thinking about it, if all of this is screwing you up, if the work is done by a gas, put a negative in front of the W. If the work is done on the gas from the world around it, leave it positive. If you ever see it written with a negative, you know why. They wrote it from the perspective of the gas as opposed to the perspective of the world around the gas. You and I live in the world around the gas, so we'll call positive work done on it. Delta U for internal energy. If that's positive, that means that our internal energy increases. And what does that mean? Well, if your internal energy went up, your temperature went up. If internal energy delta U, that change was negative, then we would say that our U decreased, which means that it took our temperature down with it because we have an energy loss. Q, heat. If Q is positive, then we have heat added. which means that energy must be flowing in from the environment. Your gas is being heated from burning gasoline or some electric heating element or the sun, whatever. There's an outside heat source putting in energy in the form of heat. If Q is negative, then we know that means that heat was removed, and that means that energy flows out into the surrounding environment. So your piston, if it is not insulated, loses heat to the environment. Occasionally, you're going to want to have heat lost not by work, but as heat. Energy lost not by work, but as heat. Why? So that your engine doesn't melt. The burning temperatures of gasoline are not too far off from the melting point of the metals used to build an engine. So if you don't have coolants, you're gonna have a rough day. W for work. If work is positive, work is done on a gas. Your volume decreases and your gas is compressed. If work is negative, then work is done by a gas, which means that your volume increases and your gas expands. Whew. Let's think of some situations, children. Let's say you hit a hammer against the head of a nail. What would the signs of these be in that situation? If you hit a nail with a hammer, what would the sign of each of these three be? Well, is thermal energy flowing in from the surroundings of the nail? No. I imagine the room and the wood and the nail are probably all at the same temperature when you start. So let's say that Q would just be equal to 0. Is work done on the nail? Absolutely. If work is done on the nail and it gets kind of compressed, the shock of it squeezes those particles inside of the nail together. If this is positive and this is 0, looking at the equation, delta U would need to be positive. So the nail must get hotter from being struck. You can try this yourself, and I assure you it's the case. Now, in all honesty, there is probably going to be friction between the nail and the wood, but that would not transfer incredibly fast. So hit the nail a couple times, touch the head of the nail before it has time to become temperature stable, and this description will work. If you give it long enough for the heat to travel up the length of the nail, then yeah, you have to worry about that frictional heating too. Another situation for you. You heat a cylinder with a movable piston slowly. Now, if you heat it slowly, the gas expands slowly, and that's going to keep the temperature constant. So as it's heated, it expands, keeping the temperature the same. If the temperature is kept the same, delta U must be 0. It's being heated slowly, so we would expect that Q should be positive. But if this is 0, and that's, the answer, Q is positive, what must be the case for work? The work would need to be negative in order to balance out the books. And an expanding gas does negative work. Last one. A high pressure gas in a well-insulated container pushes a piston out very quickly. Again, a high pressure gas in a well-insulated container. What does it mean that the container is well insulated? It means that the thermal conductivity is not going to be very much at all. So we can expect that Q, in this case, should be zero. If it's very well insulated, you don't have to worry about heat leaving through that insulation. So a well-insulated cylinder has a high pressure gas in it that pushes a piston out really quickly. Again, pushing a piston out, work is done by the gas. So energy is leaving because the work that the gas does is pushing that energy to the piston plunger to move the actuator, to move the tires or whatever. So the energy is leaving the gas because the work is being done by the gas. But without any heat coming in to replace that, we must expect that the temperature of the gas will drop, and therefore the amount of energy in it has dropped. Am I making any sense here? I'm hoping so. One last example, and then you're on your own with a practice sheet. A gas is kept in a cylinder that can be compressed by pushing down on a piston. You add 2,500 joules of heat to the system, but you also push the piston down through a distance of 1 meter using a constant 1,800 Newton force. What is the change in the gas's internal energy? Heat is added, so we're going to expect delta U to probably go up, right? Also, the distance, well, it's easy to work with, but that's a pretty big piston. The force, you are pushing down on the gas. Now, when we were doing mechanics, down was conventionally negative, but look here. We're doing work on a gas. We must be pushing it in the positive direction. And we want to know delta U. We know that energy is conserved, so the heating and the work are not creation, but rather transfer. Delta U equals 2,500 joules, and work is force times distance. 1,800 newtons times 1 meter is 1,800 joules of energy added as work, because Newton meters are joules. 2,500 plus 1,800 gives us 4,300 joules. Easy dubs. Light work, no reaction. Ain't nothing but a peanut. At this point, you guys are so good, I'm not worried about it. You just need a little bit of practice to keep your cues hot and you'll be fine. Practice sheet is coming. Internalize these lessons. Go back through the examples. Find yourself some examples of your own on Varsity Tutors or Crack AP or whatever. And do I was going to have Boba sign off, but he ran off. Adios, kids.